In this lesson, we are going to study the applications of integration. Until now, many students may think that integration only means finding the area under a curve. But in real world mathematics, integration is much more powerful than that. Integration is a method for adding infinitely many tiny pieces to understand a complete physical quantity. For example, if you want to know the total area of an irregular region, we divide it into very thin strips and add them. If we want to know the volume of a three-dimensional object, we divide it into very thin slices and add them. If we want to know the total force of water on a dam, we divide the dam into thin horizontal bands and add the force on each band. The main idea of this slide is that definite integral transforms abstract mathematics into a practical tool for modeling reality. The formula shown here represents the definite integral. We can read it as the integral from a to b of a function with respect to x. In simple words, it means we are continuously adding small quantities from a starting point to an ending point. So integration is not only a calculation method, it is a language of continuous accumulation. It allows us to model dams, machines, springs, biological growth, population change, mass distribution, and even the balance point of structures. This slide introduces three major real world applications of integration: hydrostatic force, work and mass, and population growth. The first example is hydrostatic force. When water pushes against a dam, the pressure is not the same everywhere. Water pressure increases with depth. The deeper the point is below the surface, the greater the pressure. So we cannot simply use one pressure value for the whole dam. Instead, we divide the dam into many thin horizontal strips, calculate the force on each strip, and then integrate. The formula shown in the first panel can be read as the integral of rho times w of x times s of x dx. Here, rho represents the weight density of water, w of x represents the width of the dam at depth x, and s of x represents the depth. The second example is work and mass. Work is energy used to move an object. If the force is constant, work is force times distance. But if force changes with position, then we integrate the force function. The formula can be read as the integral of x dx. The third example is population growth. When a population changes continuously with time, integration can help us calculate accumulated growth over an interval. The formula can be read as the integral of r times p of t dt, where r represents the growth rate and p of t represents population at time t. The key message is simple. Integration helps us measure things that are changing continuously. This slide explains one of the most important applications of integration: finding the area between two curves. Suppose we have two functions. The upper function is f of x and the lower function is g of x. To find the area between them, we subtract the lower function from the upper function. The formula is a equals the integral from a to b of open bracket f of x minus g of x close bracket dx. Verbally, we say area equals the integral from a to b of the upper function minus the lower function with respect to x. This formula is very logical. A thin vertical strip has a height equal to f of x minus g of x. Its width is dx. So the tiny area of one strip is height times width. That is f of x minus g of x multiplied by dx. When we integrate from a to b, we are adding all these infinitely thin vertical strips. This idea is used in many applied fields. In economics, if f of x represents revenue and g of x represents cost, then the area between them can represent accumulated profit. In physics, if one curve represents two different rates, the area between them can represent total difference over time. So the main idea is area between curves is the accumulation of vertical differences. In the previous slide, we used vertical slices. That means we integrated with respect to x or dx, but sometimes vertical slicing makes the problem complicated. If the curves cross or if the region has a shape that changes from left to right, we may need multiple integrals. In such cases, horizontal slicing may be easier. Horizontal slicing means we integrate with respect to y or dy. The formula shown here is a equals the integral from c to d of open bracket u of y minus v of y close bracket dy. Verbally, we say area equals the integral from c to d of the right function minus the left function with respect to y. When using dx, we usually think top function minus bottom function. When using dy, we think right function minus left function. This is very important. For vertical slices, the height is upper minus lower. For horizontal slices, the width is right minus left. So when solving an area problem, we should not automatically choose dx. We should first look at the shape of the region. If horizontal slicing gives a simpler expression, then dy is better. The key message of this slide is integration is flexible. We adapt the method to the geometry of the region. This slide introduces the slicing method for volume. Imagine a loaf of bread. A full loaf is made of many thin slices. If we know the area of each slice and we add all the slices together, we get the total volume of the loaf. This is exactly the idea behind volume by slicing. The formula is V equals the integral of A of x dx. Verbally, we say volume equals the integral of the cross-sectional area A of x with respect to x. Here, A of x means the area of a slice taken at position x. The thickness of each slice is dx. So the tiny volume of one slice is A of x times dx. When we integrate, we add all the slice volumes. This method is very powerful because the slices do not always need to be circles. They can be squares, triangles, semicircles, or any other shape. The only requirement is that we must know the area formula for the cross section. For example, to find the volume of a pyramid, each slice may be a square. To find the volume of a cone, each slice may be a circle. To find irregular solids, each slice may have a different area. So the core idea is three-dimensional volume can be calculated by stacking infinitely many two-dimensional areas. Now we move to solids of revolution. A solid of revolution is created when a two-dimensional region is rotated around an axis. For example, if we rotate a curve around the x-axis, it sweeps out a three-dimensional solid. This idea is similar to a lathe machine in mechanical engineering. A lathe spins a material around an axis and cuts it into a smooth object. In calculus, we do something similar mathematically. We rotate a curve or region around an axis and calculate the volume of the resulting solid. The challenge is that these shapes can be complex. They may not be simple cylinders, cones, or spheres, but integration gives us tools to calculate their exact volumes. There are three common methods for solids of revolution: the disk method, the washer method, and the cylindrical shell method. The method we choose depends on the shape of the region and the axis of rotation. If the solid has no hole, the disk method is often useful. If the solid has a hole, the washer method is better. If slicing parallel to the axis makes the calculation easier, we use cylindrical shells. So this slide prepares us for three important volume methods. This slide explains the disk method. The disk method is used when a region is rotated around an axis and the resulting solid has no empty hole inside. Each slice of the solid is like a circular disk. The formula shown here is V equals the integral from a to b of pi times open bracket f of x close bracket squared dx. Verbally, we say volume equals the integral from a to b of pi times the square of f of x with respect to x. Why does this formula make sense? Each slice is a circle. The area of a circle is pi r squared. In this case, the radius is f of x. So the area of one circular slice is pi times f of x squared. The thickness of the slice is dx. Therefore, the small volume is pi times f of x squared multiplied by dx. When we integrate from a to b, we add all the circular disks. This method is especially useful when the region is touching the axis of rotation. For example, if the area under a curve is rotated around the x-axis and the curve gives the radius, the disk method is direct and simple. So the disk method can be remembered as circular area times thickness. Add it continuously. This slide explains the washer method. The washer method is similar to the disk method, but now the solid has a hole inside. Each slice is not a full disk. It is a washer, which means a circular ring. To find the area of a washer, we subtract the area of the inner circle from the area of the outer circle. The formula V equals the integral from a to b of pi times open bracket open parenthesis f of x close parenthesis squared minus open parenthesis g of x close parenthesis squared close bracket dx. Verbally, we say volume equals the integral from a to b of pi times the outer radius squared minus the inner radius squared with respect to x. Here, f of x is usually the outer radius and g of x is the inner radius. The area of the outer disk is pi times f of x squared. The area of the inner hole is pi times g of x squared. So the washer area is pi times f of x squared minus g of x squared. Then we multiply by dx and integrate. This method is useful when a region between two curves is rotated around an axis, creating a hollow center. The simple memory rule is washer method equals outer disk minus inner disk. Now we come to the cylindrical shell method. The shell method is different from the disk and washer methods. In the disk and washer method, slices are usually perpendicular to the axis of rotation. But in the shell method, we use slices that are parallel to the axis of rotation. When a vertical rectangle is rotated around the y-axis, it creates a thin cylindrical shell. The formula shown here is V equals the integral from a to b of 2 pi x f of x dx. Verbally, we say volume equals the integral from a to b of 2 pi times f of x with respect to x. Let us understand the anatomy of this formula. 2 pi x represents the circumference of the shell, f of x represents the height of the shell, dx represents the thickness of the shell. So the small shell volume is circumference times height times thickness. That means 2 pi x times f of x times dx. When we integrate, we add all the cylindrical shells. The shell method is especially useful when the washer method would require solving for x in terms of y, or when the algebra becomes complicated. So the shell method is often a smart shortcut. It changes the way we slice the region to make the integral easier. This slide explains arc length. A curve is not always easy to measure directly. We cannot simply place a ruler along a curved path. But if we zoom in very closely, a small part of a curve looks almost like a straight line. So calculus approximates the curve using many tiny line segments. Then by adding the lengths of these segments, we get the total arc length. The formula shown here is arc length equals the integral from a to b of the square root of 1 plus open bracket f prime of x close bracket square dx. Verbally, we say arc length equals the integral from a to b of the square root of 1 plus the derivative of f of x squared with respect to x. This formula comes from the Pythagorean theorem. For a tiny segment of the curve, the horizontal change is dx and the vertical change is approximately f prime of x times dx. When we apply the Pythagorean theorem, we get the square root expression. Arc length is used in many real applications. For example, we can calculate the length of a cable, the path of a road, the trajectory of an object, or the shape of a bridge curve. The key point is integration lets us measure curve distance by adding infinitely many tiny straight distances. This slide explains surface area of revolution. Previously, we calculated volume when a region was rotated around an axis. Now, instead of calculating the full inside volume, we calculate only the outer surface. This is important in real life. For example, if we want to paint a curved object, cover a metal casing, design a glass surface, or estimate material cost, we need surface area, not volume. The formula shown here is SA equals the integral from a to b of 2 pi f of x times the square root of 1 plus open bracket f prime of x close bracket squared dx. Verbally, we say surface area equals the integral from a to b of 2 pi times f of x times the square root of 1 plus the derivative of f of x squared with respect to x. Let us understand the formula. 2 pi f of x represents the circumference created when the curve rotates around the x-axis. The square root part represents a tiny arc length element. So surface area is circumference times slanted arc length. In simple words, we are wrapping a very thin band around the surface and adding all the bands together. This formula connects two ideas, circular motion and arc length. So surface area of revolution is the accumulated outer layer created by rotating a curve. This slide introduces two physical applications of integration, mass and work. First, let us discuss mass. If an object has uniform density, calculating mass is easy. But if the density changes from point to point, we need integration. The formula shown here is m equals the integral from a to b of rho of x dx. Verbally, we say mass equals the integral from a to b of the density function rho of x with respect to x. Here, rho of x represents density at position x. A tiny piece of the object has mass approximately equal to rho of x times dx. When we integrate, we add all tiny masses. Now let us discuss work. If force is constant, work equals force times distance. But if force changes with position, we use integration. The formula is W equals the integral from a to b of f of x dx. Verbally, we say work equals the integral from a to b of the force function f of x with respect to x. This is useful for springs, machines, lifting cables, and any system where force is not constant. So the main message is integration allows us to calculate total physical quantity when the local value changes continuously. This slide explains hydrostatic force. Hydrostatic force is the force exerted by a fluid, such as water, on a submerged surface. A dam is a perfect example because water pushes against it continuously. But water pressure is not constant. It increases as depth increases. Near the surface, pressure is smaller. Near the bottom, pressure is much larger. Because of this, we cannot use a single pressure value for the entire dam. Instead, we divide the dam into thin horizontal bands. For each band, we calculate the approximate force. Then we integrate to find the total force. The formula shown here is F equals the integral from a to b of rho times w of x times s of x dx. Verbally, we say force equals the integral from a to b of rho times the width function w of x times the depth function s of x with respect to x. Here, rho is the wet density of water. Root of x is the width of the dam at depth x. S of x is the depth of the strip below the water surface. Dx is the thickness of the strip. So each tiny force is density times width times depth times thickness. This is a powerful example of integration because it shows how calculus helps engineers design safe structures. This slide introduces moments and centers of mass. The center of mass is the balance point of an object or system. If the whole mass of the object could be concentrated at one point without changing its balance, that point would be the center of mass. For flat regions with uniform density, the center of mass is also called the centroid. The slide shows two formulas. The first formula is x bar equals 1 over m times the integral of x times rho times f of x dx. Verbally, we say x bar equals 1 divided by the mass multiplied by the integral of x times rho times f of x with respect to x. This gives the horizontal coordinate of the center of mass. The second formula is y bar equals 1 over m times the integral of rho times open bracket f of x close bracket squared over 2 dx. Verbally, we say bar equals 1 divided by the mass multiplied by the integral of rho times f of x squared divided by 2 with respect to x. This gives the vertical coordinate of the center of mass. These formulas are based on moments. A moment measures how strongly mass is distributed around an axis. In engineering, centers of mass are important for balance, stability, and structural safety. In biomechanics, center of mass is also important when analyzing human movement, posture, gait, jumping, or sports performance. So integration helps us locate the balance point of continuous object. This final slide summarizes the whole lesson. Integration is not only about area under a curve, it is a unified toolkit for modeling continuous accumulation. For area, integration calculates the net difference between curves in two-dimensional space. For volume, integration builds three-dimensional solids using slicing, disks, washes, and shells. For arc length and surface area, integration measures curved paths and outer skins of rotated surfaces. For work and mass, integration calculates accumulated energy and variable density. For hydrostatic force, integration manages pressure that changes with depth. For balance, integration locates the centroid or center of mass. The final idea is very important. Whenever a quantity changes continuously and we want the total effect, integration is usually the mathematical tool we need. So we can say that integration is the language of continuous accumulation. It allows us to move from small pieces to complete systems, from local change to total quantity, and from abstract formulas to real world engineering, physics, biology, economics, and biomechanics. That is why applications of integration are so powerful. They show us that calculus is not only a subject in mathematics, it is a blueprint for understanding the physical world.